Hey, so hi there everybody. We're now in our next video on number theory, and this is going to be our second video for Diophantine equations, or shall we say the linear Diophantine equations. So in this video, we're going to show solvable LDEs, the linear Diophantine equations, and the general solution and how to take it. Actually, all these problems can be summarized in a single theorem, and which we're going to show in this video. So after that video, the one before, maybe you can see the link right beside this one, above, on the top of this video. Next is we establish a necessary and sufficient condition for the LDE AX plus BY equals C to be solvable. Its proof, in fact, provides a formula for an arbitrary solution when it is solvable. The Indian mathematician Aryabhata provided a complete solution of the LDE in two variables. Okay, so a portion of this theorem, okay, which is long but fairly straightforward, is a variation of his method. So let's present this theorem, shall we? So this is again, as I have stated, it's fairly long, but then kind of straightforward actually, provided we have the sufficient theorems and corollaries. So this is the theorem. So the theorem states that the LDE AX plus BY equals C, okay, this linear Diophantine equation here, is solvable if and only if, so we have this necessary and sufficient, okay, if and only if D divides C, where D is the GCD of these two numbers, or rather of this A and B. Okay, furthermore, if we have X sub 0 and Y sub 0 is a particular solution of this LDE, then all its solutions are given by this particular solution set. Okay, are given by this. Okay, so we have X equals X sub 0 plus B over D times T, and we have Y equals Y sub 0 minus A over D times T, where T is an arbitrary integer. Okay, so that's the theorem. You can rewind the video to if you want to restate it. So yeah, let's give a proof for this theorem. Shall we put the proof beside it, not under it? It will need some space. So let's put it beside it. Moving on. Yeah. Okay, so the purposes of this is, for us to save some slide, some part. Okay, so let's give the proof. Okay, so the proof consists of four parts actually. Let's say that the proof consists of four parts. So what are these four parts? So we will state this one by one. First part is, since we can see in the theorem that there is the if and only if symbol, so we know that we need to check the implication and the converse. The implication and the converse, the conditional and the converse. So the first is, we shall prove this, that if the LDE is solvable, then D divides C. Second part is the converse of this. So if conversely, if D divides C, then the LDE is solvable. Number three, what will be the third part? So we have the equations there. We would want to prove that they are indeed solutions for the LDE. So we say that X equals X sub 0 plus B on D times T, and the other one, Y equals Y sub 0 minus A on D times T, is okay, or are solutions of the LDE, are indeed solutions of the LDE. Number four, what will be the fourth one? Every solution every solution of the LDE is of this form here, x and y, is of this form. Okay, so we will be proving each part one by one in that order, in this specific order. So 1, 2, 3, 4, 5. Okay, so let's start. Okay, this is gonna be a long plate for us. Okay, so for number one, again, we want to prove that if you want to show it again, number one, the LDE is solvable, then D divides C, and then for number two, it's converse. If D divides C, then LDE is solvable to for us to really say that it is necessary and sufficient. That is if and only if. The if and only if. So for the first part, um, okay, for the first part, let's have to prove for number one, to prove each part, rather to prove that if the LDE is solvable, then D divides C. Let's have this. Okay, suppose we have X is equal to alpha and Y is equal to beta. It's a solution. So let's suppose this is a solution indeed, let's say. And uh, then we have A alpha plus B beta equals C. Since we have our original LDE, the linear LDE, is AX plus BY. So we let alpha as X, beta as Y. So we have this. Okay. Since D is equal to the GCD of A and B, okay, so since that is true, so therefore we can say that D divides A, since it's a GCD, D divides A and D divides B. D divides B. So by theorem 3, or rather 1, 2, 3, yeah, theorem 3, okay, if I can remember it correctly. So by theorem 3, the one which tells us about the linear combination in our videos, by theorem 3, we say that D divides A alpha plus B beta. This is the linear combination theorem. Okay, maybe you can watch the theorem 3 before this, or visit it right after. So that is to say, if this is true, that is to say that D divides C. Okay, since C is equal to A alpha plus B beta, and then we saw that by theorem 3 we applied that D is the GCD of A and B. So if that's the case, so therefore D divides A, D is a factor of A, and D is a factor of B also. So by theorem 3, linear combination, this is it. And then we therefore say that since this is equal to C, therefore D divides C. Okay, that's the end of theorem 1. I'll just put a line so that to say that it's under one theorem. One proof rather. Okay, for our second proof, um, we shall prove that the converse. To prove that if D divides C, then the LDE is solvable. Put it here. So we will have. So what we'll have is, say, suppose D divides C, and that is what we want to suppose first. Then we know, since um, D is a factor of C, so therefore C is equal to D times certain E. Okay, for some E. For some integer E. For E. Now, since we know again, since D is equal to the GCD of A and B, so by theorem, by the theorem we talked about last in the linear combination. If you can remember that, I think that is a theorem from Euler, if I can remember it correctly. So by the theorem based on Euler, I think it's really on one of our videos in linear combination. Okay, in linear combination. So there exists. Okay, therefore there exists a certain R and S. Okay, such that R A plus S B equals D. This is by the statement of the theorem that if the GCD, okay, if the GCD is equal to this D, therefore there exists some R and S in such a way that it is a linear combination, okay, of that numbers. Okay, so if you want me to state the theorem, I can say it again. The GCD of A and B is a linear combination of A and B. So let me restate that. Um, recall, just a recall. Okay, recall theorem by Euler. I'm pretty sure this is one from our video in linear combination. Okay, so please check that out. So the theorem by Euler states that the GCD of A and B is the linear combination. Linear combination of A and B. Of A and B. Okay, there. So that's a theorem that we say. So this is a GCD. Okay, since we have the GCD of A and B, so therefore it's a linear combination of A and B. So therefore there exists some R and S such a way that we can write it as a linear combination. Okay, of A and B in this part. Okay, so that's part of the theorem that states that that is true. Let's put it there. And then we will be moving forward to our proof since we know that. So therefore, okay, therefore, move this up. So therefore, we say we will need to multiply. Okay, multiply, multiply both sides, multiply both sides of this equation by e. So which yields it will yield us this equation. So it will give us RAE, as you can see, RAE plus SBE equals DE. Equals DE. So that is, this is the time. That is, as you can see, we suppose that D divides C. So therefore, C is equal to DE. So if we can see that we have a DE here, okay. So since C equals DE, so therefore we can regroup, get the A out. So we have A times RE plus B times SE equals C. So therefore we can see that thus from this we can see that this is now X. This can be an X, this can be a Y. So we have somehow like an AX plus BY equals C kind of a LDE. So thus we can say now, sorry, thus X sub 0 is equal to RE and Y sub 0 is equal to SE, is a solution of the LDE. Is a solution, oops, is a solution of the LDE. Of the LDE. So that is, so to say, that is, it is solvable. Since there's a solution, so yeah, it's solvable. Okay, so that's the end for our part 2. Okay, that's the end for our part 2. You may review the video if you want. If I will be reviewing, so that will be quite long. So let's go back a bit. a bit. I need more space. So this is the first part of the theorem. Oops, sorry. This is the second part of the theorem, or rather the first part. So let's try to put the third part over here. Okay, here you go. So for number 3, we want to solve this time to show that every um rather to show that x equals x sub 0 plus b on d times t, and y equals y sub 0 plus a on d times t is a solution. So we need to show that it is a solution. So what we have is, let's go back to the original part. Let's go back to the original part. So we have here ax plus by. So we have ax plus by equals a times x sub 0 plus b over d times t. Okay, plus what we have is b times y sub 0 minus a over d times t. Okay, so what happened here? So since we say that x is equal to x sub 0 plus b over d, we simply literally substituted the x here, and literally substituted the y here. So as to make it this form. I'm sorry that it's this is a minus a over d. Okay, so moving forward, we will try to what do you call that? Manipulate this second part. So I will do this step by step. Okay, I won't be skipping anything so that it will be clear. 0 plus a times b over d times t plus by sub 0 minus b a over d times t. We want to group together this one and this one, and we will be putting these together, this two. Okay, so if we do that, what do we have? We have a x sub 0 plus b y sub 0 plus, let's make it a b over d times t minus a b over d times t. As you can see, they're actually the same exact terms, so we can cancel them out. Okay, we can just cancel them. It will give us 0, and what we have in the end is a x sub 0 plus b y sub 0, which is actually, of course, this is literally just the same with ax plus by. Okay, so this is equal to c. So to say, um, we can write it here, equal to c. So therefore, as to say, ax plus by is equal to ax sub 0 plus by sub 0 is equal to c. So thus, by what is shown here, thus, x equals x sub 0 plus b on d times t, and y equals y sub 0 minus a on d times t, okay, is a solution. Is a solution for any integer, for any integer t. Okay, so that's the third part. Again, if you want to repeat that process, kindly just rewind this video or rewatch this video. To save time, let's proceed to the fourth proof. So this time we will be showing. Okay, we want to show to show that every solution x prime y prime is of this desired form. Is of this desired form. What do we mean by desired form? By this form, okay? So for every solution x prime and y prime, it should be on this form. So we will be showing that in this proof. So since x sub 0, y sub 0, and x prime, y prime are solutions of the LDE, are solutions of the LDE, we have this. So a x sub 0 plus b y sub 0 equals c, and similarly we have ax prime plus by prime equals c. So they're just the same. Basically, it's in the form of ax plus by equals c. So let's equate the two c's since c is equal to c. So we say that c equals ax sub 0 plus by sub 0 equals ax prime plus by prime equals c. Actually, you can just erase the c in both parts. What we will want to show is put all the a's on one side, put all the b's on one side. This time we will be deleting the equals c. Okay, that's trivial. So we have a x. Let's delete first a 0. By sub 0 equals ax prime plus by prime. To make it clear and better to see. Oops, better to see. Uh, okay. Now we want to put the x prime as a positive. So let's transpose this x sub 0 to the other side. Let's transpose this y sub 0, b y prime to the other side. So what we have is, what is left is by sub 0 minus by prime equals ax prime minus ax sub 0. Isolate the a's and b, so we have b times y sub 0 minus y prime equals a times x prime minus x sub 0. Now, what we want to do is to divide both equations by d. Okay, so in this step, what we'll do is divide both equations. Oops, both equations by d. So if we have that, what we'll have is actually um, b over d times y sub 0 minus y prime equals a over d x prime minus x sub 0. So we will be needing two powerful theorems here. Actually, some of them we haven't talked about, in fact. So we will be using a theorem which states that okay, let me use another color of the pen to illustrate that. Okay, so by one theorem that states that this is a theorem. Oops. Okay, so by one theorem, it states something like this. We will let the GCD of A and B to be equal to D. Then we say that the GCD of A over D and B over D is equal to 1. Okay, so by this theorem, we'll continue. Since we said that the GCD of A and B is equal to D, therefore the GCD of this A over D and B over D, literally here, is equal to 1. So by this theorem, by the theorem above, let's just use that for now. There's no number. By the theorem above, um, the GCD of A over D and B over D is equal to 1. So by another corollary, so this is actually a corollary again. by Euclid. So let's just erase this so here. Let's use that later. So we'll have a corollary. Oops, wrong. It's only one R. Corollary. Corollary. It states that um, if A and B are relatively prime, and if A divides BC, then A divides C. Oops. So this is the corollary. So if A and B are relatively prime, so the GCD is 1, which it shows here. And if A divides BC, meaning we have B and C, there's a multiple. The B this is a multiple of B, which means we multiply it by some certain C. Therefore, it states that A is divisible, or no, A is a factor. A divides that certain C, which is a multiplier to the factor of B. So from this corollary, we can say that B divides D. Okay, B divides D over here. So since we know that D in this part, okay, since we have relatively prime, it's D divides B and A. Therefore, B divides B alone. Okay, and then we'll put that in this side. Okay, B divides since we have A, okay, here, so we will put it in this side. Let's kind of move a little bit to the right. There's no more space. Okay, so using that corollary. Okay, so by using that corollary by Euclid, actually that's a corollary by Euclid. So by the previous corollary, that's attributed to Euclid. Actually, I forgot to write that down. We say that B divide B over D, okay, divides this x prime minus x sub 0, and hence x prime minus x sub 0 is equal to B over D times a certain t. Since this B over D is a factor of x prime minus x sub 0, so therefore this is equal to this one factor times a certain factor to make it like that. So we will call that t for some integer t. Well, this is part of the proof still. Um, for some integer t. So that is to say um, x prime is equal to x sub 0 plus b over d. I forgot this should be x sub 0. B over d times t. Okay. Now substituting this x minus x sub 0 in the equation. Okay. Substituting this x minus x sub 0 in the equation, what we have is the equation is let me write it down now. Substituting for x prime minus x sub 0 in our original equation, in the equation, let me write it down. I mean the equation. Okay, so now substituting for x prime minus x sub 0 in the equation, I mean the original equation, the very much original, so without dividing it by d. So remember this equation, a x a times x prime minus x sub 0, okay, equals b times y sub 0 minus y prime. Okay, so substituting here the value of x prime minus x sub 0, what we mean by this value is this value here. So since we have that, what we have here is actually we got as ourselves a times b over d t equals b times y sub 0 minus y prime. Okay, so we want to we can see that we can we can from here we can divide both sides by b. So to cancel out the b's here. So this is continuation. This is the next part. So we can see that we can divide both equations by b, and then that nothing will happen. So we have a over d times t equals y sub 0 minus y prime, which in turn to say that y prime transpose the y sub 0 to the other side is equal to y sub 0 equals, or rather not equals, minus a over d times t. What we did actually is transpose the y sub 0 to the other side. That's going to become negative. Multiply the whole equation to make the y sub 0 positive. So what we have is this. What we have is this, which is actually the pair. Okay, the pair. Let me use the blue one. The pair of this solution here. Okay, so yeah, that's it for this proof, for the fourth proof. Now let's just restate our conclusion for the overall proof. Let's just restate that. Lastly, okay, at last, we can restate it. Okay, at last, okay, thus, okay, thus, every, oops, sorry, every solution, every solution of the LDE is of the desired form. Desired form. That's the end of theorem 4. So by the first, second, third, and fourth part of this theorem, the proof is complete. The proof is complete. Okay, so yeah, this is a pretty much long video, but I hope that you carried it out. So this is, at least we have the proof of this theorem, of this LDE is solvable, and it has this what we call now the general solution. So these desired forms that we saw a while ago are what we call the general solutions of any LDE. Okay, of the form ax plus by equals c. Okay, so this is the best part to end the video now. Thank you very much for watching. I hope you were with me in the whole video. Yeah, don't forget to like and subscribe to my channel. Well, thank you very much. See you soon. Bye.